Hello everybody. In this video we are going to be looking at the solutions to the college prep reflection and mirrors homework problems 11 through 15. Let's get started with problem number 11. It tells us that a concave mirror has a radius of 20 centimeters. A 2.0 centimeter tall object is 30.0 centimeters from the mirror. The first thing they want us to do is draw a ray diagram to show the location and orientation of the image. So we have our ray, or our I'm going to try to say that again. We have our concave mirror right here. This is my concave mirror. Remember, in concave mirrors, the reflective surface is on the inside of the curvature. And we have our object right here. Remember, we always represent our objects with arrows. It just makes our lives easier. So there are three different types of rays that we can draw. And if you guys watched the PowerPoint, you should know what they are, but let me just review those with you. If I have an incident ray that goes from the object, remember we always draw our incident rays from the tip of our arrow. And that way I know that the reflected ray is going to go through the tip of the image of my arrow. So my first incident ray is parallel with the principal axis. So here's my first ray that is parallel with the principal axis. If I have a ray that is parallel with the principal axis, the reflected ray is going to go through the focal point, which is denoted by the F there. So now we can see that this reflected ray reflects back through the focal point. My second ray, my incident ray, is now going through the focal point. So now my incident ray goes through the focal point. And when that happens, the reflected ray that comes off of that incident ray is going to be reflected parallel with the principal axis. We see on this blue ray, and I just have them color-coded just so we can differentiate between them. We can see that my incident ray is going from the tip of the arrow, from right here, from the tip of the arrow through the focal point, and then when it reflects off the mirror, it's going to be parallel with the principal axis. On my first ray, the incident ray is parallel with the principal axis, and the reflected ray goes through the focal point. My third ray, let me do a couple of erasures here just so that I don't make too much of a mess. My third ray goes through the center of curvature. So we can see that my first ray goes through the incident ray, I should say, goes through the center of curvature. And when that happens, it's going to strike the mirror at a 90-degree angle and it's going to reflect back on itself. So my third ray goes through the center of curvature and then it hits the mirror here. And then when it hits the mirror, it's going to reflect back on itself and go back through the center of curvature. So those are my three rays that I can draw. And I can always draw those rays because if I know where the center of curvature is and the focal point. Where all of those reflected rays intersect. Now where the reflected rays intersect is where my image is. And because all of my incident rays came from the tip of the arrow, where the reflected rays intersect shows where the tip of the arrow or the image of the arrow is going to be. So I have my first reflected ray that's going this way. I have my second reflected ray that is going here. And I have my third reflected ray that is going up here. And they all intersect at a point right here. And that is where my image is located. Let me just erase some of that stuff. And we can see that we always start drawing our image from our principal axis. So the base of the arrow is always on the principal axis, and the point of the arrow is where my reflected rays intersect. So from this, I can see that I have a real image, that it is inverted, and that it is reduced. Reduced just means that the image is smaller in size than the object. Inverted just means that it's upside down, and it's real because my reflected rays actually go through this point where the image is located, or where the image appears to be. So the reflected rays actually travel through that point. That's what causes that to be a real image. Part B of problem 11 asks what is the image position. So they want to know where the image is located in relation to the mirror. So I know that the radius of the mirror is 20 centimeters. So that is my radius of curvature. I know that the object is located at 30 centimeters away from the mirror. So that is my object distance. So this is d sub o, and this is the radius of curvature. The focal point, or the focal length, is halfway between the radius, or the center of curvature, and the mirror. So the focal length is half of my radius of curvature. So my focal length is going to be 20 centimeters divided by 2, which is going to be 10 centimeters. To find the image distance, I know I need to use my mirror equation. And when I take my mirror equation and I solve it for the image distance, I'm going to get the image distance equals the focal length times the object distance divided by the object distance minus the focal length. Now I can plug my values for the focal length and the object distance into that equation. And when I do that math out, I'm going to get an image distance of 15 centimeters. Now, because that is positive, I know that the image is going to be in front of the mirror. So I know I'm going to have a real image that is located in front of the mirror. And if you look at the ray diagram that we did in the previous problem, you'll see that is in fact the case, that my image is located in front of the mirror, and it is a real image because the reflected rays go through the point in space where the image appears to be. One more note on the mirror equation. Notice I did not need to convert from centimeters to meters. In the mirror equation, we don't need to do that because we don't have any constants or any other derived units in it. It's just straight distance units. So it doesn't matter if it is meters or centimeters, it will all cancel out and come up with whatever unit that I'm using. So I just keep things in centimeters, make our lives a little bit easier. Part C asks, what is the image height? So to find the image height, I know that I'm going to need to know what the magnification is. I know the magnification is equal to the image height divided by the object height, which is also equal to the negative of the image distance divided by the object distance. So when I want to solve for the image height, so I'm solving for image height, and when I solve this part of the equation for the image height, I know I'm going to have the image height is equal to the negative of the image distance times the object height divided by the object distance. Now the image distance we got from the previous part of the problem, that was 15 centimeters. The object height, which we are given right here, is 2 centimeters, and the object distance is given right here at 30 centimeters. And when I do that math out, I'm going to have an image height of negative 1.0 centimeters. So the negative sign tells me that the image is inverted. So the image is inverted, and if I look at my object height, which was 2 centimeters, my image height is 1 centimeter, so it is going to be smaller. And once again, if we look at the ray diagram that we did in the first part, we will see that we do get a smaller image and that it is inverted or upside down. Problem 12. An object is 36.0 centimeters in front of a concave mirror with a 16.0 centimeter focal length. Determine the image position. So we are given the object distance, or the distance of the object from the mirror, which is 36 centimeters. We are given the focal length, which is 16 centimeters. Boo! I don't know if you guys can hear, but the wind is howling out there. All right, and let's see. Something just flew by, but I think it was one of my daughter's Barbie doll pants. Yeah, it looked like a little pair of jeans that belonged to a Barbie doll. Just went scattering across the floor. All righty, so much for the entertainment. What are we looking for in this problem? Where am I? What am I doing? Where am I? Oh, okay. We are looking for the image distance. So how far is the image located from our mirror? We are going to start off with our mirror equation, and we are given the focal length, we are given the object distance, and we are being asked to solve for the image distance. So let's isolate the image distance and solve for that variable. And I'm going to take you through this one step at a time just to show you how we rearrange this formula. So if I want to solve for the image distance, I need to get that all by itself on one side of the equal sign. So that means that I want to take my fraction 1 over object distance and subtract it from both sides. And when I do that, I'm going to have 1 over the image distance equals 1 over the focal length minus 1 over the object distance. Now, things are blowing all over the place here. What are we getting, a hurricane? I'm going to have to go close some windows here. This is like, I might be in Oz by the time I get to the end of this problem. All right, I'm already in Oz. All right, yeah, you guys are my munchkins. I'm losing my train of thought here. This is just terrible. All right, let's keep going. So when I do that, we solved for that, and we isolated the image distance all by itself. Now I want to take this, and I want to reduce it down to one fraction. So when I do that, I want the lowest common denominator, so that's going to be f times d sub o. And when I do this formula, I know I have it f here, so I want to multiply my numerator here by d sub o, and I'm going to have d sub o. And then we have a minus sign there. And then for this part of the fraction, I'm going to multiply this by f, and I'm going to have d sub o minus f. So to neaten all of that up, I'm going to end up with 1 divided by the image distance equals the object distance minus the focal length divided by the object distance times the focal length. Now the next thing I want to do, and this is the tricky part, my unknown is still in the numerator here, so I need to get that into the denominator, and essentially all I need to do is flip both of those fractions around. And when I do that, this will flip, and I'm going to have the image distance equals the object distance times the focal length divided by the object distance minus the focal length. And I plug up my values for the object distance and focal length into that equation, and I'm going to have an image distance of 28.8 centimeters. I'm going to go close some windows or just check the forecast or something here. Problem 13. A 3 centimeter tall object is 20 centimeters from a 16.0 centimeter radius concave mirror. Determine the image position and the image height. So what are we given in this problem? We are given the height of the object, which is 3 centimeters. We are given the distance of the object from the mirror. So the object distance is 20 centimeters. And the radius of curvature is 16 centimeters. We are being asked to find the image distance and the image height. First thing I need to do is determine the focal length. So I know the focal length is going to be 1/2 of my radius of curvature. So 1/2 of 16 centimeters is going to equal 8 centimeters. Now that I know my focal length and I know my object distance, I can find the image distance, and I'm going to do this the same way I did in the previous problem. I'm going to start with my mirror equation, and I am going to rearrange it until I have successfully solved for the image distance. And again, that's the same exact procedure that we went through in the last problem. Now I can plug in my values for the object distance and the focal length. And when I do that out, I am going to have an image distance of 13.3 centimeters. Now to find the image height, I know that the image height divided by the object height is equal to the negative of the image distance divided by the object distance. Solving that for the height of the image will give me the image height equals the negative of the image distance times the object height divided by the object distance. I plug those values into the equation, and that will give me an image height of negative 2.0 centimeters. And once again, I have a negative value for the image height, excuse me, so I know that it is inverted and it is smaller than the object height, so I know that it is reduced. Problem 14. A concave mirror has a 7.0 centimeter focal length. A 2.4 centimeter tall object is 16.0 centimeters from the mirror. Determine the image height. This is a repeat of the previous two problems. We're going to solve it the exact same way. As with the other problems, we are given the focal length, which is 7.0 centimeters. We are given the height of the object, 2.4 centimeters. The distance of the object from the mirror, 16.0 centimeters, and we are looking for just the image height. So in order to find the image height, I know I am going to need the image distance. It's not explicitly said that I need to find it, but I do need that to find the height of the image. So I'm going to start with my mirror equation. Once again, solving that for the image distance, and doing that is going to give me an image distance of 12.4 centimeters. Now that I have the image distance, I can solve for the image height. Once again, do it the same exact way I did in the previous problems. I'm going to start with my magnification formula, solve it for the image height, and plug my boy. I think my common sense was taken away with the wind, just like the Barbie pants. All right, plug all of my values into that equation, and that will give me an image height of negative 1.9 centimeters. And once again, it is a reduced image, and it is inverted. Problem 15. An object is near a concave mirror with a 10 centimeter focal length. The image is 3 centimeters tall, inverted, and 16 centimeters from the mirror. What are the object position and the object height? So we've changed it up a little bit on this one. We are giving you the location and the height of the image, and we are asking you to find the distance and the height of the object. So in this problem, we have our focal length of 10.0 centimeters. We have the image height, which is 3.0 centimeters tall, and it is negative. And I know it is negative because I'm told that it is inverted. So we have an inverted image, so it's going to be a negative height. And we also have the image distance of 16 centimeters. We are being asked to find the object distance and the object height. Once again, I'm going to start with my mirror equation. I'm going to, again, solve it the same way, but now rearranging for the object distance instead of the image distance as we did in the previous problems. All the math is exactly the same, and we get something very, very similar to what we had before. So the object distance is going to equal the image distance times the focal length divided by the image distance minus the focal length. Plug my variables into that equation, and I am going to have an object distance of 26.7 centimeters. Now to find the object height, once again, starting with my magnification formula, but now solving for the object height, and that will give me the object height equals the negative of the object distance times the image height divided by the image distance. Note in this one, I do have a negative sign here and a negative sign here that will cancel out. So when I do out the math, I'm going to get a positive 5.0 centimeters. And my object height is always, or the object should always be upright to start with. So I should have a positive value for the object height.